So now I want to talk about a topic from pure mathematics, which is related to my own research in number theory, which is prime factorization in number fields. So let's start from the basics and build up to what this means. So we are familiar with the integers, which we denote by z, which is, whole numbers and their negatives. And we are familiar with the primes, which, let me just say, are integers that can't be written as a product, except for the trivial way of writing, for example, 1 times b. So these are 2, 3, 5, you're familiar, hopefully. So I want to introduce a slightly more general notion of integers and primes and see where that leads us. So an algebraic integer is any number which is a root of a polynomial of the form x to the n plus constant times x to the n minus 1, etc., where, first of all, you will notice that the coefficient of the highest term is 1, which is to say that your polynomial is monic. That's just a word for that. And we require that the coefficients are integer coefficients. So an algebraic integer is a root of a monic polynomial with integer coefficients. So, for example, the square root of 2 is an algebraic integer. It is a root of the monic integer polynomial x squared minus 2. Fair enough. Why do we call these things integers? Well, they're in some sense analogous to the regular integers that we're used to. And one way of seeing this is that even though we have made this more general definition, and we're allowing new things like square root of 2, things like 1/2 is not an algebraic integer. So, maybe there's no need to prove this, but it's a fact that 1/2 is not the root of any monic polynomial with integer coefficients. The idea is basically like, it would have to be, if you want integer coefficients, you need to have some coefficient on your highest term. So this is what it means to be an algebraic integer. And they're supposed to behave like a more general set of integers. For example, consider the set z square root 2, which is the set of everything you get from the integers with throwing in the square root of 2. It turns out that you can write all of them like that, where a and b are integers. So let's just take a moment to see that we can still do all the same things with these things that we can do with our regular integers. So we can still do arithmetic. for example, if we take, so what do elements of this set look like? They look like things like 1 plus 2 root 2, or 3 plus 4 root 2. And we still can add and multiply these things perfectly well. So this, if we want to multiply these, we should just FOIL it out. This is 3 plus 6 root 2 plus 4 root 2 plus 8 times root 2 times root 2, which is 8 times 2. And then we can just collect things back to put it back in this form, which just means combining these two terms and combining these two terms. And we just get, I think, 19 plus 10 root 2. So we can still multiply things, and we can still add things, and we can still, since we can do these things, we can define prime in the same way. If it's not a product, if it can't be written as a product. Again, with some trivial exceptions. And the question is, in this new set of integers, z square root 2, what are the primes? So let me take a minute to answer a question from the chat. Does an algebraic integer necessarily have a representation in terms of radicals? So that is a very interesting question to a number theorist, and it requires some technical machinery to solve. But the answer is no, you cannot always represent it in terms of radicals, but there is a very nice condition for when you can. Or I should say, yeah, there's a very nice condition in the sense of abstract algebra that tells you when you can. It's a very beautiful theory, but yeah, I will have to save that for another time. So let's return to our question. We can define primes just the same way if it can't be written as a product. And this is supposed to be some kind of analog of the integers, so it's natural to ask, what are the primes in this new setting? And one way that we can approach this problem we can find all the primes in this new setting by considering what happens to the primes from our old integers. So what I mean by that is every prime in the normal sense, so I'll call these primes in Z, will either, so first of all, it could stay prime in Z root 2, or it could split into two prime factors. In Z root 2. And basically, these are all the things that can happen. The reason that you'll get two prime factors at most is because you're taking a second order root. So that corresponds to the fact that it's a square root. If you took a cubed root, you might get 3 prime factors, and so on. But it's true that either of these things could happen. Some of our primes will stay prime, and some of our primes will factor. So the updated question is, how do we tell which primes factor? So I'm using factor and split to mean the same thing. And I don't think I'm going to prove this precisely, but I'll try to give some indication that this is the truth. The answer, but okay, I think you will also find it convincing because it's a very satisfying answer. The answer is P a prime splits in Z adjoin root 2 exactly when there is a root 2 mod P. So let me put that in quotes, but what I mean is 2 is a square mod P. So this is a very satisfying condition because it tells you that the splitting behavior of this prime in, these more general integers basically depends on this other way that the prime interacts with the particular algebraic integer that we chose. So there's something very, very nice and symmetric about this that I appreciate. But let's look at some examples. So 2 is a square mod 7. In fact, 2 is equal to 3 squared. Let's use congruent rather. Mod 7. 3 squared is 9. That is 7 plus 2. So 7 should split. And indeed, 7, you can check, is equal to 3 plus root 2 times 3 minus root 2. Basically, since you're doing a plus b times a minus b, when you FOIL this out, you'll get 9 minus 2, which is 7. And you'll notice that this 3 appearing here, this is not a coincidence, but I don't think, so it's not always going to be quite that simple. It is always going to be related. You can use, so basically this is why this is true. If you have a solution here, you can figure out from that what the factors will be here, but there's not a very clean way of writing it down in general. But you have a clear indication that that is what's happening here. And as an example in the other direction, 2 is not a square mod 5. We've done this a number of times, but let's just check again. 0 squared is 0. 1 squared is congruent to 1. 2 squared is congruent to 4. 3 squared is congruent also to 4. And 4 squared is congruent to 1. So none of those are a 2. 2 is not a square mod 5. So 5 stays prime in Z root 2. There is no way of writing it as a product, and you can check that for yourself if you like. So this so this is the answer to our question in this particular case of Z square root 2. But the question is much bigger than that. Or I should say giving a systematic answer. For any algebraic integer, so we chose square root of 2 for this example, but we chose we could have chosen any algebraic integer whatsoever. So for any algebraic integer in place of square root 2, giving a systematic answer in this generality is a motivating problem for large areas of number theory. And by a motivating problem, in case those words aren't familiar, what I mean is that this is a problem that is basically, with the current technology, considered to be impossible to solve. It's beyond reach. But sort of working towards this problem is an inspiration for a lot of big areas of number theory. So in addition to describing this problem, I want to give a more classical number theory example. So the question is, when is a prime a sum of two squares? This is a very classic flavor of number theory, which is basically just trying to understand basic questions about how arithmetic works in the integers. So when can you write p as a sum of two squares? Or really any number, but you can reduce the question to primes in particular. And the connection to write p as a sum of two squares, you cannot factor this in integers, but if you allow yourself to use algebraic integers, you can factor this expression into a plus bi, or let me not use I, but let me say root minus 1 times a minus b root minus 1. So square root minus 1, sometimes called I, is the imaginary unit. It's an imaginary number, it's a complex number. So it's certainly not an integer, it's not even a real number, but it is a perfectly good algebraic integer. In particular, it's a root of x squared plus 1. So we can factor this using the square root of -1. And what this tells us is that p is the sum of two squares exactly when p splits in z root minus 1. How nice is that? And furthermore, we can use what we know, well, we can use what we've said, what we've claimed about these types of integers to actually give an even better answer to the problem. So we've seen this is when -1. So the claim is that the same thing happens in this situation that happened in the last situation. The last situation, we used the square root of 2, and we saw that something splits exactly when 2 was a square mod p. Now that we're using the square root of -1, a prime will split exactly when -1 is a square mod p. And using a little bit of our knowledge of number theory, we can turn that into the following theorem. -1 is a square mod p. If and only if p is congruent to 1 mod 4. Or when p is equal to 2. But 2 is a scoundrel and does not like to play by the rules. So if you do number theory, you will often find yourself having to write, deal with the case p equals 2 separately, because 2 is quite special. But in general, for odd primes, -1 is a square mod p, if and only if p is congruent to 1 mod 4. So I won't prove this fully, but I'll do one direction. So suppose that -1 is a square mod p. So a squared is congruent to -1 mod p. And we want to show that p is congruent to 1 mod 4. So first of all, we can write a to the p minus 1 is congruent to 1 mod p. This is just from Maslow's theorem. But since we have a squared congruent to -1, we can rewrite this also a to the p minus 1. So p minus 1, if p is an odd prime, then p minus 1 is even, so we can divide it by 2. This is a squared, the p minus 1 over 2, and a squared is congruent to -1. So let's just swap that out. This is -1 to the p minus 1 over 2. And now equating the right-hand side of these two formulas, right-hand sides, we get -1 to the p minus 1 over 2 is equal to 1. So just to mention, these are congruences, but since this thing is either plus or minus 1, and we're saying it's congruent to 1, it must be 1. Because -1 is not congruent to 1 unless p is 2. So equating the right-hand sides, we get -1 to the p minus 1 over 2 equals 1. So p minus 1 over 2 is even. Because when you take powers of -1, if you take an odd power, you get -1. If you take an even power, you get +1. We got +1. We must have taken an even power. And from here, you can say it's just a little bit of unwinding to show that that's equivalent to what we want. So p minus 1, since p minus 1 over 2 is even, p minus 1 is divisible by 4. And if p minus 1 is divisible by 4, then p is congruent to 1 mod 4. So the other direction is, not horrible, but maybe a little bit harder. I won't go through it. But this is a nice peek at, first of all, the sort of questions that number theorists care about. And second of all, the power of modular arithmetic for addressing these questions and giving sort of patterns and systematic answers to how integers behave.